I'm Herb Gross, and welcome to lecture number 2 in our Gateways to Algebra series, where today we'll continue talking about what I prefer to call our prelude to algebra. You may recall that last time we ended with the statement that if all there was to algebra is what we did last time, how come it takes so long to learn algebra? And that's what I want to start discussing today. But before that, I want to bring up something that came up after the lecture was over yesterday, and I think it's worth responding to. Remember, we were talking about pick a number, multiply by 2, add 3, write the answer. The question came up, why would anybody ever say to you, pick a number, multiply by 2, add 3, and write the answer? And I thought, what I'd like to do is to start with that and sort of review briefly to show you how practical applications and formulas lead to the input-output program syndrome. So let's look at what we were doing last time. What we said was what? Pick a number, which we called the input. Then the program was what? Multiply by 2, add 3, and then the output was write the answer. Now, let me give you an example where something like this might come up. Suppose you're ordering cheese from a catalog. It's Christmas time. You want to get cheese for some friends. You have a catalog from some cheese company, and what they advertise is $2 per pound, and then it says $3 for shipping and handling. Now, suppose you wanted to buy 6 pounds. What would you do? You would take the number of pounds, multiply by 2, add 3, and the answer would be how much it would cost. So, for example, the input would be 6 pounds. You're multiplying by 2, that would give you 12. You add 3, that would be 15, and the answer would be 15. Now, that's arithmetic in the sense that knowing the number of pounds, multiplying by 2 is something you can do on the calculator. Adding 3, you can do in the calculator. Hopefully, you can do it in your head. But what I mean is there's nothing tricky about this. The algebra comes in when you start with the 15. If a person says you have $15 to spend, how much cheese can you buy? When you reverse the steps, notice that add gets replaced by subtract, multiply by divide. So in other words, you would say what? 15 subtract 3 is 12. And from a practical point of view, all that's saying is, let's get rid of the shipping charge because I can't buy any cheese with that. That $3 is wasted. I only have what? $12 left to spend. Each pound costs me $2. So what I must do is what? Divide the 12 by the 2. In other words, to undo multiplying by 2, we divide by 2, and the answer then comes out to be 6. By the way, the next thing that happens over here is, did you notice how long it was to write this down? So what we do in algebra is we invent a shortcut notation again. The input we said was x. Then we said what? When you multiply by 2, you just put the 2 down next to the number. And now the next thing you do is what? You add 3. So, and then you write the answer, and we decided to call that y. So what you have over here, and notice the difference here. If you're afraid of symbolism, this bottom line here, y equals 2x plus 3, looks a little bit scary. On the other hand, saying pick a number, multiply by 2, add 3, write the answer, looks pretty simple. The thing is, I want you to practice enough to learn, like in a foreign language, how you translate from one language into another. I want you to practice with starting with this, how do you get this? And starting with this, how do you get this? Now, the first thing that happens down here, if you start with this, is notice that 2 different things are happening to the x. On the one hand, the 2 tells you that the x is being multiplied by 2. On the other hand, the 3 tells you that you're adding 3. You can't do both of these at the same time. Which one should you do first? Well, if you look at the program, you're told to multiply by 2 first. So what we do in algebra is to indicate what's being done first, we use parentheses. In other words, we look for the variable, the letter that's scrambled with the numbers. When we locate it, we have to remember what? Everything within the parentheses names the same number, is one number. By the way, that's tricky. Here's what I want you. For example, 2 and 3 are 2 different numbers, aren't they? But when I put a plus sign between them, that is only what? One number. 2 plus 3 is 5. See, x stands for a number, 2 stands for a number, but 2 times x is just one number. The parentheses tell you what? start with x, multiply by 2, and then add the 3. See, if I wanted to add the 3 first, I would have said what? Start with x, add 3, and now what do I want to do? I want to multiply this whole thing by 2, so I put the whole thing in parentheses because that's what I'm multiplying by 2. By the way, if that seems strange to you, I want you to understand that you already know this in a different context from English grammar with the use of hyphens. Let me see if I can show you a little bit more about what I mean by that. Look at this phrase over here, the high school building. Pause on this for a moment and ask yourself, can you see two completely different meanings for this phrase? You see, what I want you to see is that you could be talking about a one-story building called the high school, or you could be talking about a college a building that's 15 stories high. And you're talking about what? The high school building. Now, what we do in English grammar is if you want high school to be one word, you put a hyphen between high and school. If you want school building to be one word, you put a hyphen between school and building. In mathematics, among other reasons, we don't want to use a hyphen because it looks like a minus sign. In mathematics, we simply use parentheses the same way as in English you would use a hyphen. For example, in mathematics, if we want high school to be one word, we just enclose it in parentheses. In other words, this and this mean the same thing. If we want school building to be one word, we simply enclose school building in parentheses, so that this and this would have the same meaning. So do you sort of get the idea on that? You see what I'm saying? Don't be afraid of the new language. You just have to get used to it. And here again is the beauty of the videotape. If you said, gee, it makes sense when he says it, but I'm not quite comfortable with this yet, what should you do? Stop the tape, pause it, rewind it, whatever it takes to get you comfortable, then you can pick up again from where we just left off, just by pressing the stop button again. Now, let's see, again, let's just practice now how we're going to read this. See, this is just a review of what we did before. Here's the mathematical statement, and what does it say over here? It says what? Let's see if we can translate now. We look for the variable that's scrambled in with the letters, that's with the numbers, that's the x. So we're going to start with x. We're inside the parentheses, so that has to be done first. What's happening? We're adding 3. Now we're through with the parentheses. What's happening outside the parentheses? There's a 2. What's the 2 doing? Well, there's no arithmetic symbol, so it means what? Multiply by 2. And then it says what? The equal sign means what? The answer is y. So in an algebra book, you might see somebody say, find the value of y when x is 6, and all that means is what? If you start with 6, you're going to do first what? Add 3, multiply by 2, and the answer would be 18. And notice again the difference, that if we had written 2x plus 3 and had grouped it this way, all that would mean is what? Start with x, in this case 6, multiply by 2, that would be 12, add 3, the answer would be 15, and notice that changing the order of these two steps already makes a difference. And that's another thing that we have to realize in our algebra course. Algebra requires a meticulous knowledge of language. Changing the order of two statements changes the entire meaning of what's going on. And that's why we have to be careful of how we group things. You see, when you've written out the steps, you can see what step comes first. But when you, how do we say it in society? There's no such thing as a free lunch. When you invent the language of algebra, everything becomes compact. But the importance of every single symbol becomes even more important. Let's see if I can show you another example this way. Here's something I've written down over here. Look at this now. Of course, this already starts out as an eyesore. You see that there are two sets of parentheses. Actually, it might have looked better if I had made the two sets in different colors so you could see what goes with what. But actually, an even better thing to do is it's not the shape of the grouping symbol that's important. It's basically whether we recognize them or not. In other words, I don't have to keep using parentheses. What I've done over here, for example, is what? I've used parentheses and brackets. And the reason for doing this is when you see a whole bunch of parentheses, it's hard to match them up. But if you see a parenthesis over here, you're looking for a parenthesis over here. When you see a bracket over here, you're looking for a bracket over here. So let's see how you would read this. I won't take the time to write this whole thing out, but let's see if you can practice reading this with me and see what's happening over here. What's the first thing we do over here? We look for the letter that's scrambled in with the numbers. That happens to be what? X. Where's the X? It's inside the parentheses. So we have to do everything inside the parentheses first. See, don't multiply by the 2 first, because the 2 is outside the parentheses. This is hyphenated. So whatever X is, and that's the input. You pick whatever you want. What does this tell you to do? Start with X, add 3. What do you do next? You've used up the parentheses, but you're still inside the brackets. Being inside the brackets, you have to do that next. So after you start with X, and you add 3, and you multiply by 2, that's what you're going to do. Then what do? Now you're all through with the brackets. You look outside the brackets, and that tells you to do what? Add 5. In other words, when all is said and done, this is just another way as to how, if you had taken the program that we had just used before, I don't know if I have that written down. Well, we can write it again. See, what this says is what? If you started with X, and then you add 3, and then you multiply by 2. If after you did all this, you now wanted to add 5, see how clear this is? It tells you exactly what order to do these steps in. This is how you'd have to write it in the language of algebra. And see, again, notice how crucial the grouping symbols are, as I'll show you in a moment. By the way, also, just because this is math doesn't mean that we don't want to be efficient and what have you. We like to be able to avoid the grouping symbols wherever possible. And so we make up certain agreements. And I want to underline the word agreement because there's no logic to it. It's simply something we agree to do in the name of expediency, in the name of simplicity. What we say is, look, in this problem, look what happened over here. We either could have multiplied by 2 first or added 3 first. And therefore, we had to use grouping symbols to tell us which to do first. The agreement is going to be, let's always multiply before we add. There's no logic to this. All it says is what? Whenever you see a bunch of numbers with pluses and times, you start with something and keep grouping together until you come to a plus sign. In other words, if I had down 3 times 5 plus 4 plus 7 times 6 times 2, what I do is I start grouping over here. See, I'm going to do all the multiplications first. So what's going to happen over here? The 3 and the 5 are being multiplied. I'm only going to stop when I come to a plus sign. See, so the 3 times 5 is being multiplied. Then it's plus 4. I'm still adding over here. What's being multiplied? The 7, the 6, and the 2. So when there are no grouping symbols, I'm going to read it as if it was written like this. Okay? Now, what that means is what? Over here, do I have to use the brackets? Let me show you why I don't. Let me leave the brackets out and assume I'm using this agreement. Based on this agreement, what's happening over here? Remember, everything inside the parentheses is one number. We don't worry about that. What's happening to the parentheses? It's being multiplied by the 2. There's also a 5 being added. Since there are no grouping symbols, which one do we do first? The first one we do is we multiply. So the 2 will be multiplied by the x plus 3, and so by not having the brackets in there, it was the same as if we really did. The thing we have to be careful of, going back to our statement that there's no such thing as a free lunch, once we put that agreement in, we have to be careful. Notice the danger over here of saying, oh, 7 plus 3 is 10, I'll just replace 7 plus 3 by 10. No, you can't do that because look at the variable over here. What's happening? It's being multiplied by the 3. What operation do you do first when there's no grouping symbols? You multiply first. In other words, the fact that there are no grouping symbols over here means you're starting with x and then multiplying by 3. Then you're adding the 7. If I wanted to add the 7 and the 3 first and then multiply by x, I would have to put the 7 plus 3 in parentheses, and then put the x over here. And by the way, this gets bigger and better, and that's another reason why algebra becomes more and more complicated. And that is, we can string together larger and larger expressions. For example, let's take a look at this and see how we would read this. Again, notice how scary this looks if you look at it as one long piece. But how are we going to do this? We look for the x. The x is inside the parentheses, so we do that first. This says what? Start with x, add 2. Now what's happening to the parentheses? We're either going to multiply by 3 or add 4. But since there's no grouping symbols here, it tells us what? Multiplication comes first. So we start with x, add 2, multiply by 3, add 4. See, now we add the 4. Now what's happening? We've taken care of the brackets. The brackets are being both multiplied by 5 and adding 1. Again, no grouping symbols, so multiplication is done first. So after we've added the 4, the next thing we do is multiply by 5. Then we add the 1, and then what? Since the 6 is multiplying the entire braced expression, that's the time that we multiply by 6, okay? Now, what happens is this. If I give you the input, notice what happens. We work from the inside out. If I give you the output first, now it becomes trickier. You see, the problem is the output is obtained after you've done all of this to the input. So this now becomes like a game that we have to get used to. It's called capture x. How do you capture x? Whenever x is inside a grouping symbol, it's being protected by that grouping symbol. So to be able to get at x, you first have to get rid of everything that's protecting the grouping symbol that's protecting x. Let me start that with a simpler illustration to show you what I mean. So this is called an algebraic equation. See, an open sentence in which the blank is a numerical situation is called an equation. This says what? Start with x. In fact, let's write it out. Start with x. Then what we do? Add 3, multiply by 2, and the answer is 18, isn't it? Well, how can we work backwards here? To undo multiplying by 2, we divide by 2. 18 divided by 2 is 9. Instead of adding 3, we subtract 3, so it must mean what? 9 minus 3 is 6. It means if we put 6 into the parentheses here, this should be a true statement. Let's check it. 6 plus 3 is 9, times 2 is 18. Well, see, the way of doing this, without having to write all these steps out, is to say, look, we want to capture the x. The x is being protected by the parentheses, therefore we have to unbind the parentheses. What's blocking the parentheses? The 2. What's the 2 doing? It's multiplying the parentheses. How do you undo multiplying by 2? You divide by 2. If I divide by 2, the 2 drops out. I'm left with x plus 3. But if I divide the equality by 2 on one side to keep it balanced, I have to divide by 2 on the other side. 18 divided by 2 is 9. So if this is true, this is true. Now do I have x by itself? Not quite. Almost. To get x by itself, I have to get rid of the 3. What's the 3 doing? It's being added. To undo adding 3, what do? Subtract 3. And by the way, isn't that what I did right over here? If I subtract 3 from this side, I get x. If I subtract 3 from this side, I get 6. So what we call solving an algebraic equation is nothing more than reversing the order of starting with a number and getting to the answer versus starting with the answer and getting to the number we picked. And you see, we can do stuff like this. See, let's just take a look. See how complicated these recipes can become? This says what? Start with x, multiply by 3, add 4, multiply by 6, add 12, divide by 9, subtract 2, divide by 2, the answer is y. If I start at the top with any number, don't I just have to do plain old arithmetic to get to the answer down here? Let's start with 4 just for the fun of it. I start with 4, I multiply by 3, that's 12. By the way, people say, how'd you know enough to start with 4? I start with any number I want. It says start with x. X stands for any number. I just happen to start with 4, okay? Somebody else says, why couldn't we start with 15? Well, you could have. We're just going to do that next. We start with 4, multiply by 3, the answer is 12. Add 4, the answer is 16. Multiply by 6, the answer is 96. Add 12, the answer is 108. Divide by 9, that makes this 12. Subtract 2, that's 10. Divide by 2, that's what? 5. And so the answer is 5. If you started with 15, notice that the program is exactly the same. You would still do what? Multiply by 3, add 4, multiply by 6, add 12, divide by 9, subtract 2, divide by 2, the answer is y, which would be 16. The algebra part comes in when somebody tells you, oh, the answer is 8. What number did I start with? By the way, just in terms of a Goldilocks and the three bear analogies, we want the answer to be 8. Notice what happened. When we started with 4, we got an answer that was too small. 5 is less than 8. When we tried 15, we again guessed wrong, but 16 is bigger than 8. That tells us what right away? It tells us that the number that we're looking for has to be more than 4, but less than 15, and that tells us how to solve this by trial and error. But watch how nice the algebra works. To undo dividing by 2, you're going to multiply by 2. To undo subtracting 2, you're going to add 2. To undo dividing by 9, you're going to multiply by 9. And by the way, if you have trouble with this multiplication, you can use a calculator. To undo adding 12, you're going to subtract 12. To undo multiplying by 6, you're going to divide by 6. To undo adding 4, you're going to subtract 4. To undo multiplying by 3, you're going to divide by 3. And what did you wind up with? 7. In other words, if you started with 7, the output would be 8. And by the way, here's one more interesting thing before we stop this example. When you started with 4, the answer was 5. When you started with 15, the answer is 16. When you started with 7, the answer is 8. Is it possible that whatever number you start with, the answer is going to be one more than that? Certainly it seems true so far, but as I'll show you in a later lecture, what happens so far doesn't tell you what's going to happen later on. But you see, here's another role of algebra. Is this a coincidence, or will it always happen? That's another reason we study algebra. Here's another reason. I'm just going to change some wording slightly over here. It says what? Start with x, subtract it from 15, and the answer is 9. If you're careless, you're going to confuse this with another problem that we've already done. Doesn't this almost look like start with x, subtract 15, and the answer is 9? Notice the difference between saying subtract and subtract from. That's kind of interesting. You say, what difference does it make? Well, let's try it with this problem here. Let's use the reasoning that we've used before. We said the answer was 9. When was the answer 9? It was after we subtracted it from 15. Therefore, what should we do next? You might say, oh, let's add it to 15. If I add 9 to 15, what do I get? I get 24. If I start with 24 and subtract 15, I certainly will get 9. But what happens up here? If I start with 24, be careful of the wording. This says start with 24, subtract it from 15. That's not 24 minus 15. That's 15 minus 24. And we haven't had this yet, and that's going to motivate our next lecture. 15 minus 24 is going to be known as negative 9. But the important thing is there a right answer to this problem? What number must you start with in order that when you subtract it from 15, you get 9? In terms of a practical example, if you have $15 saved up and you spend part of it to buy something, and after you buy it, you have $9 left, what amount did you spend? Wasn't that $6? Let's check it. Start with 6, subtract that from 15, that's 9. Okay. Now, that's the answer, isn't it? It's not 24. Evidently, if you start with the answer, how do you undo subtracting a number from 15? Believe it or not, you still subtract it from 15. It turns out amazingly that the opposite of this statement is the statement itself. Look, start with 9, subtract it from 15, what answer do you get? 6. Now, you say, that doesn't sound right. See, the trouble with intuition is that as long as it works, it's great. When your intuition leads you to something that's wrong, it doesn't mean that there's anything wrong with your intuition. It simply means what? That what you believed intuitively didn't conform to reality. So the real power of algebra and why it takes so long to learn is that whenever we come to something that either stymies our intuition or is too complicated for our intuition to do comfortably, we want to try to find what? A way of paraphrasing, translating, transforming that problem into one or more simpler problems that lead to the correct answer. And that's basically what we're going to be dealing with. But next time, and the few times after that, we're going to have to take a little vacation from the algebra, which is good. It'll give you a chance to have this stuff sink in. And what we're going to talk about are signed numbers, because, you see, without signed numbers, there's basically no hope that we're going to be able to do great work with simplifying certain statements. It's not because we like signed numbers, it's because what? We need them. And we'll talk about that more next time, but until next time, what? Keep studying, work hard, stay young.